In today's lab, we're going to focus on boundary conditions, and some of the different options there are, and observing and learning how to understand the impacts that they have. So let's take a look. Key objectives today are to practice analyzing a local geometry of interest or region of interest, learn about the behavior of different types of load and displacement conditions that you might apply as boundary conditions, and practice looking at stress patterns and thinking about whether they make sense in terms of what you know about basic stress models, such as bending and axial and transverse shear. And then we will compare the model to calculations. In this video, I'll walk you through the general processes of doing the FEA, and you look to the handout for specifics about what you need to turn in and the calculations to do. This is the geometry we're going to be looking at. As a planar bar, its cross section is 20 millimeters by 5 millimeters, and it's relatively long, over basically half a meter long, and I don't really want to mesh the whole thing just to look at the stresses around the holes where they're going to be highest. And so what we could do is trim this off and put on statically equivalent loads using St. Venant's principle, and then analyze it, and we should be able to get out some good estimate of the results or the stresses in those regions. Now, in this case, there's not a lot exciting happening here. We really want to focus on different ways of putting loads and constraints on the part. When we apply this, you can see we could solve for the reaction forces, which I've already done for you at the pins, and then we could also solve for the shear and moment at this face where we cut the bar. Now, it might be tempting to apply both sets of forces and moments, all that, to the model. But in practice, we need to either apply constraints at the holes and then put the shear and moment, or fix the face, the cut face, and apply the loads at the forces. That allows the computer program to solve for the balance. Just like the solar cell, if we didn't get the rounding just right in our number forces, then it won't be balanced and it will not be able to solve. We'll have pivot errors. So we want to apply some constraints. And again, I'm going to demonstrate it showing one approach, and then you're going to solve it showing the other. Okay, let's open up Workbench and get started. Okay, so here we are in Workbench. I've opened up a static structural case. We'll need to first start by importing the geometry. And we have I've created one that has some faces split in SolidWorks so that you can look at different ways of controlling the geometry. Now, I do want to go back just to get the practice. As we've done the other cases, I want to create a custom material. I'm going to do that real quickly here using the properties that are in your handout. Okay, so we have our engineering data, we have our geometry, we're ready to open up ANSYS Mechanical. Okay, so here we have the geometry. You can see we've got just a rectangular bar. You'll notice that one end is longer, has farther distance from the holes than the others. That end over here on the right, as I have it positioned, is going to be our cut face. So for this case, what I want to do for mine, I'm going to constrain this right face and apply reaction loads to the holes. You'll do the vice versa. You'll constrain the holes and apply reactions on the right face. Now, as usual, we're going to come through here. We'd start with our geometry. We notice this has it defaulted to the structural steel. I'm going to go ahead and select the other one. Again, this is good practice just to check those, but it's not really critical to the actual analysis we're going to do today. Now, we'll follow on down there. We see I need to set my mesh. Good first step is just to generate the default and see what it looks like. You can see that indeed it's pretty coarse. It's a hexahedral mesh, which is efficient. I think I'm going to lean into that and just start refining the mesh size. I'm going to pick 2.5 millimeters. Actually, I'm going to take that back. So I put a 0, I put it back to default. We'll leave it at default initially so we could solve and make sure it does, everything kind of looks right, and then we'll get our mesh. It's nice to have a quick solution while we're trying to figure out our boundary conditions initially. So let's proceed along. For static structural, we got the question mark there. Obviously not everything's set. So let's come in and we're going to, I want to fix this face and then apply boundary conditions to the holes. Now, let's start for starters, we'll just select fix. And I'm going to select all those faces and hit apply. Now, I split those in SOLIDWORKS by putting a plane in there and using the split line function. And that'll come in handy for a second option I'll show you in a few minutes. Now, to put load on here, again, we'll just do the easiest one, and we'll just pick a force, and I'm going to select the face. Oh, I can't select both of them. I want to select just one of them. So this one I'll apply. I need to specify a direction. So let's see. This is minus 1188. Okay, it wants a vector, so I need to give a direction. So I'll click on there, and I will select an edge going the right direction. Now that's going up. That's actually the same direction I want, so I need to change this to a positive 1188. Okay, so I have one set. Now I can add a second force, and again I'll select the face, hit apply. Now I'm going to change show you the other option is I can select components. So rather than have to select a vector, I could say, oh, this is aligned to the y-axis. And so I could set that and say I want that to be a minus 1088 newtons. And we see that that's input there. So we've got my forces, and I have my displacements. Let's add in my solution data. So it's often nice to see equivalent stresses. And we haven't talked much about this, but the equivalent stresses really help us tell about, we use equivalent for comparing based on a failure mode, which we'll talk about in Chapter 5. Now, I could choose Mach's principle, but I really want to, if I want to think and understand these stresses, I want to think about them in terms of my coordinate system. So let me choose my normal. I know I'm going to have bending in here. So bending with the axis along the x-axis, I should expect to see most, my bending stress should be sigma x. That was the default. If I needed to, I could select other ones, but we'll leave it at that. Notice I could also have other coordinate systems if I define them, which we haven't. So I've got a normal stress, and I also expect to see transverse shear. So let me plot a shear. Transverse shear would be in the tau xy. So you can see that is the default option, but again, I could select any of the others. So I have those three, and then it could be helpful to see my deformation in terms of understanding what is happening. Okay, so we've got two forces. Support should be fully constrained. I have my data. Let's solve the problem. Okay, so we're looking at our distribution. The displacements are pretty smooth, as we might expect. Let's look at our shear stresses. One thing that stands out to me, we've got some local peaks here, a little bit of things that currently aren't resolved well enough that'll be improved by the mesh. But I do see a lot of shear in between these two, um, and not as much out here. Uh, I'll leave that to you to determine whether that is correct or not. Look at my normal stresses. I see compressive on the bottom, tensile on the top, with about 0 in the middle, which is indicative of bending. That looks promising. So, good first pass. At this point, I would go back through and revise my mesh and try to get a little bit better quality mesh. And I want to check to watch to see if my stresses are resolved. So, are converging. So let me just check what my normal stresses are. So the peak, I'll plot my maximum. Now that's showing me an issue right there, isn't it? My maximum is at that edge, which it should be high, but I wouldn't expect the maximum to be there. And of course, as we've talked about, that's kind of what happens when you have a fixed support. Now, I'll go ahead. Let's go ahead and replace that with a better constraint system. So this time, let's do support. I'm actually going to say let's apply a displacement. Okay, so we'll put a displacement. Now I'm going to select. I'll select all of those faces. Apply. Now, the biggest constraint I don't want it to move is in the x direction. So let me set x equals to 0 across that whole face. And the y and z are free, which allows it to move. That's showing it, making it more realistic there. Now, by itself, that would still allow it to rotate around the x-axis and translate in y and z. So I need some additional constraints there to make it stable. Now, because there's not a lot of force there, I just need a little bit. And so what I'm going to try to do is add an additional displacement. And I'm going to use these split faces. So if I select an edge, shift select, Okay, so I selected both of those. Oh, I got one of them selected. Honestly, not sure why it's not letting me select both of them, but rather than fight with it, I'll just do it twice. So that this middle point, it's right in the center, so there shouldn't be any strain in the y direction, any transverse strain. So I'm going to set the y 0, and then I'll just duplicate that, and then select the other edge. Okay. So, and it might be helpful to rename these. So 0y, we did this to 0y2, and we'll put this 0x. So it kind of helps me to understand what constraints I applied. And now let me create a new displacement. Again, I'm not allowing me to select both of those. So we're going to set here, I'm not going to have any z displacement around this. I don't expect any. So we'll set 0 there. And then we'll duplicate that and select this face, apply it, and we'll rename them. Okay, so let's solve that and see if that resolves my high stress in the corner issue. That was fast. It's a, okay, now we can see that my max has moved over here. There's no unusual peaks here. Maybe something unusual going on right in these corners, but that's in a low stress region, so I can accommodate that. And you can see kind of the utility of having a split face to be able to select smaller features, though it does also impact the meshing. That's contributed to the fact we have two elements to the thickness here. But we like that anyway. So let's go back and adjust our element size. So let's do a 5 millimeter elements. This is, oh, actually this is 5 millimeters thick. So let me do 2.5 millimeter elements, and we will generate the mesh, look at it, and then, you know, it's looking pretty good. It's interesting that it only split one side. Since this is planar model, and this is just a stepping stone, I'm not going to worry too much about that. Let me go ahead and solve. Right-click Solve, so we can see what the impact on the stress is. Okay, so here we've got our stresses. I'm going to line this up a little bit. So we have a stress state, and it's, you know, the max is kind of where we want it to be. A couple things I want to note. First, I probably want to write down this maximum, 137.6 MPa, and I'll put down a little note, 5 millimeter mesh, and then we'll kind of check that again to see if it's converging. Not surprisingly, my equivalent stress is pretty similar since that dominates. Shear stresses are much lower. One thing I want to show you, sometimes it's nice to be able to hold an orientation, even as I change my model, move it around, so I can come back to it and get consistent images. So under the image, there's an option of adding figure. This figure will be generated so that we could do the same for each one of these. I'll just show you what that allows me to do. If I can come back here, I can reorient my mesh, look at this a different way. If I can come back to the figure that's in that thing, I come back to this plot and the figure. So you can find one or more of those. That'll help you have some figures that are really consistent in orientation. And when you're ready, then you can always export that image to file as you've done before. Okay, so we've got those defined. Let's go back, change my mesh. I'll cut it in half, and we'll see how we're doing on our way to convergence. I'll solve that and then restart the solution, the video. Right, so that solved pretty well. And what we'll note here, I think I said it was 5 millimeters last time, but it was 2.5 millimeter mesh, and I got 137.6. I refined that, cut it the mesh in size, and went to 137, basically 138.0. That is plenty converged for the comparisons we want to do. So the only other thing I might check is look, for example, at the shear stresses and see, you know, there are, in terms of the magnitude, there's some more local things happening around the shear stresses. If I really needed to get the maximum around these holes, I'm probably going to need to refine it more, because you see these stresses have some sharp gradients across one element. And we also see a little peak there. However, this is, our main goal is just looking at patterns on this. So I would leave it easy so you could do fast iterations, and you could even back up and go to a little bit coarser mesh. You could also try doing your meshing a little bit differently than this, using tetrahedral by, you know, putting a refinement or size elements around the holes, but we'll, in addition to the global sizing. But I'll leave that up to you. This is an easy solution that works pretty well. Okay, let's talk a little bit about what we're seeing in the stresses. Here I'm looking at my equivalent stresses, which combine some of everything. Again, we're seeing at this center point, there's some funny business coming on, but I'm not too worried about it since it's away from my regions of interest. I can see that, let me switch this. I can see that there's not a peak stress at the boundary conditions, so that's not going to throw me off too much. If I come back to my normal stress, again, my peak, remember, if you want to see your peak, you click on the maximum up here. My peak is over here. It's kind of where we might expect it to be, where we've got a lot of bending. Um, Once we hit the hole, the bending stress starts going down. There's some interaction with this hole that might be moving it up a little bit to the right from where we would think of from a hand calculation, but it looks very reasonable. And if I look at my shear stresses, and we see more shear stress here than here. Look at your shear moment diagram and see if that makes sense. We do see it's higher in the middle, which is kind of what we expect from transverse shear. And we can probe it and look at what these values are. Your hand calculations aren't likely to predict things near the hole, but we can see what there is away from the hole. Now, we showed you in the process of getting to this point 2 different ways of fixing that right face. Now, I want to consider different ways of applying the load to the holes. So initially, we did just applied a force. And if we look at the normal stress here, we see that there is, well, I guess it's really hard to tell what exactly is happening. This is about 0. We've got some bending. But I believe with that force on there, it's just spreading it around the whole face, which would not be realistic, right? In essence, we want to simulate a bolt, which would just push across one face. So there's a separate type of boundary condition for that. So let me suppress these. Well, let me show you another way to do this. So if we come back into Workbench, we could do static structure, copy it over, and I'm going to apply the same, I'm going to apply the model, drop it on the model, and it's going to come across and connect all of those and leave these parts blank. If I come back into Workbench, it created a second set down here. So now I can insert new displacement and force conditions. So I wanted to set new conditions here. So let me select that area. So let me say I want to apply a bearing load, which is meant to simulate, as you see if we hover over this, radial forces acting in a hole. So, and you can even see from the plot that it kind of realistically varies where it's highest right underneath the surface. So I apply the face, and again, this was 1080, 1088. Do some components. So we'll do, so I don't want to make it a parameter. Make this y would be 1088. Right. And then I'll add a second bearing load. Select the other face, apply, switch it to components, and we'll put that a positive 1188 newtons. Okay. And I'm going to recreate the same boundary conditions on the right face, but you'll need to watch me do that a second time. So I'll pause. Actually, I'm going to show you something I found. I can actually copy this, and because everything's the same model, I can paste it there. I could copy, I could paste, right? So I made that pretty quickly. We could also see that these share the same mesh, the same geometry, same materials. So there's a lot of things that are in common. I could probably copy and paste these other down here. So you can see I get all of my solutions really quickly. I recreate this, and it even copies the figure there. So that would allow me to have a consistent result between the two cases. And let's see, so we've got my bearing loads. It looks like I'll pause this and solve both cases. Okay, so we have the solution. If we look at what we had before, our equivalent stress, let's look at our normal stress. We see the answer about 1.38, 138 megapascals with this peak there, and very symmetric, right? It's the negative of that on the bottom. When we switch to the bearing load, let's take a look at that stress. Let me go to the figures, so have the same format. And now we see that the stress on the bottom didn't change very much, but it went up on top. And the location of the peak also shifted a little bit to the left. So go back to the other one so you can see that. Now, that's probably makes sense because the stress, if you think of the path of the stress in here, if it's pushing up on here, the stress is kind of coming up and around. So there's going to be some extra stress at the top of the bar. And there's essentially some stress concentration effects that are happening from that hole in that region. So you can see in this case, it changed the results just a few percent, but it could be significant in some cases, particularly if the hole were larger. So it's important to recognize some of these different ways that these solutions behave. So your opportunity is to explore different settings. Now, I'm going to go ahead and just show you maybe just a couple other little tidbits that can help you. First, on mine, we could insert in the solution a probe for force reactions. So I'm going to select, and I have to select it for each boundary condition. So we'll just say I'm mostly interested in the X, and actually I'm probably mostly interested in the Y. So let's do the Y. That's only half of it, so it's a little bit hard to see. Let's see. So let's add another one. We'll insert probe, force reaction, and do Y2. And then we'll insert probe, moment reaction, and so the main moment's going to be taken by the 0x. Okay, so we can come up here, right click on that, evaluate results. We look at our moment, and you can see it plots it on there, shows the moment about the z-axis, and I can come over here on there and I can get the magnitude of that. And so you can see what the values are. I can also look at my forces. Here it's split across two parts. So we could, and my max and minimum, since I only have one time step, are the same. So that can be a useful way of checking my boundary conditions and making sure my answers are correct. So I'm going to give you the option of starting from my Workbench file archive so that you can have an easier time starting up. To do that, we're going to open up the file. I've saved the archive in my downloads directory. You probably want to do it someplace else. But it'll probably be called Lab 3 Student Start. So if we open that, it's going to give me a chance to name what the files were. And you can name your own thing. Like you say Lab 3 in BC, put my initials in there. Okay, so it's telling me that the project is open from an archive file. It doesn't have all the solutions. That means I'm going to have to recalculate it, okay? That's fine. And now probably, so I could just come in here and clear the generated data. And I might need to do that again for the other part of the model. Yeah. So I'll clear the generated data. That way I could restart it, and then I can begin, and I'll just need to solve the model and maybe remesh the model when I get started. So that'll give you a bit of a quick start. For your work, you could start from these prior models I have, and we could just, dropping out the original model, uh, we could drop another static structure. You see it code over there. If we come into mechanical, now we've got a third group of data down there. And again, that'll inherit my mesh and my geometry, my material properties. So I just need to apply my criteria. Now, I don't want to copy any down there because you're going to be applying a force and displacement on this edge. So if we come in here, so you want to insert, if we do a displacement, I could accept, and I'll select all these faces in there. So we apply, and we have, so we could do a Y component, and I'm going to put in, so you can put a value. I'll just put 1 in there. You can need to figure out what the appropriate value is, and then insert a moment. Let's see, there we go. We get it from here, insert moment. So again, we could go and select all the faces. We'll put 92.1. My vector now is going to be an axis. But first of all, let me apply that selection. Oh, I think I lost it. So we got to remember to hit apply on the geometry selection here. So I forgot that. So we could define our direction. It's the axis. So if we want to rotate around the, so click on there. Let's see. I probably could check that cylinder. It's just choosing the axis, I believe. But just to be safe, I'll just choose one of these lines. It's right here on that face. Okay, so that's showing a negative z. So you might have to swap that around, so it was the right direction, depending on what you determine for your analysis. So now I'd have moments, and then if I'm thinking about constraints, so we look into the supports. A couple options you might want to compare. You could do a fixed display constraint, and then there's also the cylindrical support. And so I could select this. And in the instructions, it tells you to select just half of it. Depending on what file format you use, it may split that cylindrical face, which it could be helpful in this case. It randomly seems to split it in the right spot. Or you could go in and divide it in the original geometry. I don't think you really want to do that for this, but you could select this. Notice that it starts out defaulting by all the motions fixed, so you can also drop down one of these and make them free. So you could you select that. So that would be one option. Another option would be a compression only support. I have not tried that in this case, but that could be an interesting one to apply. So again, we could select our surface. And see what they do. These get a few constraints. You could fix them entirely, and the other option is that you could do a remote displacement. Now, none of these, you may find problems a little bit with each of these, and don't worry too much about that. What I want you to see is that they are different, and maybe understand a little bit what's happening. Now, the other thing that you could do to explore this and understand a little bit better is in our analysis settings, we could set up multiple time steps. So this is static structural, so the time only has, it's not real time. It's just like points where it analyzes it. For stability in solving the solution, it often will ramp up the load until it gets to the total value, and I'll call the end of a time step. Now I can come in with my moments, and we have here, if I go to my tabular data option, I can set the magnitude to different values. So if it starts out, so we have 3 time steps, so 0, so we could have it go to 1, and then I can have it go back to 0. Oh, that's going to think I want to interpolate. So I'm going to keep those 2 constant. Then I could go to my, oh, did I apply a displacement on that face? We want to apply a force. Sorry. So let's delete that. Let's insert a force and put a magnitude of 1. And you obviously will need to choose a direction, make sure that's correct. But if I come in here, I could also come over here, tabular. You notice it's already displayed. So I could have this be 0, 0, and then be 1 there, and 1. Okay. What that does is this is going to have 1 time step where I have moment but no force, 1 time step where I have both, and then a 3rd time step where I just have the force. So I could come down and we'll just insert a Max principle. Actually, insert a normal stress and insert a shear stress here. When I start moving quickly, sometimes I forget where to see things. And I don't see things right in front of me. But we'll insert those, and we notice we have time, the time to display. So one of these, I could do 1. I could duplicate, call that 2, and then duplicate, call that 3. And similarly, I could duplicate. And so this, for example, would allow you to see what's happening in a with different loads. And you could test what we talked about in class. Is there really 0 shear stress in the XY plane when there's a pure moment applied? And that can help with understanding. So that may be something that you want to try as well. Great. I'm going to, I hope you have some fun exploring this. We're going to give it to you, the starting files, in a format that makes it as easy as possible, so you don't have to do a lot of rework with them, and you can focus on understanding these questions that we have. Good luck and have fun.